Okay, good afternoon, everyone. So we have gathered here to hear uh, KAJINO Mizuo-san. He is from Meteorological Research Institute of Japan. So this is like the IMD of Japan, Meteorological Department, and he's a professor there. But he has also he was also involved in Akash project, which involved I mean, the post-monsoon fire. You have heard of the crop residue burning, which affects the Delhi's air quality. So he conducted a number of use models for simulating those, and then they also had some ground team. So they did some validation work, which and other optimizing emissions. So he'll be talking about his research results, and this talk is also part of our Science Day celebration. So I would, without further delay, ask Kajino-san to take the stage if we are ready by then. I request people in the back, they can come forward just a bit, especially the last rows.
Yeah, I don't have this option.
We have a lot of seats out here, so you can come and grab them.
Yeah, there should be some this kind of option. There should be. So can I use my computer? Sorry, I cannot delete the AI translation. So,
Okay, he will take it.
but I have to do it from my.
I think it's okay. It's not a big problem.
Really?
It's okay.
Ah, okay. Yes.
It's not.
Yeah. Sorry for that. Sorry for the trouble. Yes.
If you are ready, we can start the session. So the stage is yours. So he'll be presenting on impact of post-monsoon crop residue burning and optimizing the emissions using that. So the stage is yours.
Thank you very much. Good afternoon. My name is Mizuo KAJINO from Meteorological Research Institute, Japan. So I'm very thankful to Dr. Manish Naga-san and Priyanka-san, Srivastava-san, to invite me to Alice here. And yes, so let me start. I have 20 slides today, so I hope it's not so much today, but each slide has many contents, so let's see. So this is, my presentation is based on the paper, which is in revision. And very strange. Okay, let me proceed. Yes, and I want to go to the next slide. The mouse is here, but actually mouse is somewhere here. This one is that one is conflicting. So yes. Sorry, here, AI computation. Post. Yes. This. Okay. Mm. Oh, yeah. It's not shared on Zoom. Maybe I can share the whole screen. Mm. Yeah. Yes, yes, yes. Mm. And then, okay, yes. Yeah, perfect. Yeah, thank you. Mm. Yes. Mm. Okay. So, thank you for the patience. And okay, today I have here is a table of contents. Introduction, my recent activity. So it's a aerosol cloud measurement at the Mount Tsukuba Observatory. We have mountain observatory also, but this is much lower than here. And the main topic is Gash project led by Sachiko Hayashida and Pradil Patra. And in the final slide, I'm suggesting some possible collaboration with you here and us. So my introduction. So I'm from Meteorological Research Institute, Tsukuba City. So I don't know if how many people knows about heard about the city, but anyway, Tsukuba is a science city constructed in 60s to 70s, and it's 40 minutes by train from Tokyo. And there are 29 governmental institutes and universities, including National Institute for Environmental Studies, where Naja-san and Priyaka-san worked before, and university, and totally 150 institutes, including private companies, and more than 10,000 researchers are working in the city. And MRI is one of the governmental institutes belongs to JMA, which is counterpart of IMD in India, and 130 researchers working for atmospheric science, oceanography, seismology, and volcanology. And University of Tsukuba has a cooperative graduate school system with those institutes. So they are collaborating with 29 research institutes. And there are 136 professors, including me, and 68 associate professors in this city, in the city. And this is the location of Tsukuba. Yeah. So Tokyo and Tsukuba, 40 minutes by train. And inside Tsukuba, here's MRI. And beside MRI, there's Nice where they worked. And then 20 kilometers in the north, there's a Mount Tsukuba. It's an isolated mountain with a height of 800 meters. And there is some fruit road there. And there's many fruits from winter to autumn, like strawberry, grape, pear, chestnuts, and apple. So we can go and eat. Yes. So, and here's a brief bibliography of mine. So I studied as a master and PhD in Kyoto University, a graduate school of geoscience in Japan. And my doctoral thesis is environmental acidification caused by the eruption of Miyakejima volcano. So, and at that time, Miyakejima volcano emit sulfur dioxide, almost half of the amount emitted from all China. So it emit a lot of SO2 from the point source. And then the precipitation was acidified near the region. So this is my study. And then I moved to Professor Yutaka Kondo's laboratory, the black carbon guy, in the University of Tokyo, and I was a postdoc. And then since 2010, I worked at MRI. And my main job there is the technical support for photochemical smog forecasting model operated by JMA. So based on the simulation result, including data simulation and forecast and statistical post-processing, then we can have the smog guidance for tomorrow and the day after tomorrow, whether the oxidant will be high or not. And also, as a research, I do numerical study on air pollution and aerosol cloud radiation interaction using NHM-Chem model. So please interrupt if you have questions then during my presentation at every moment. And NHM-Chem is JMA's regional non-hydrostatic meteorology chemistry coupled model. And the NHM is the previous generation of weather forecast model. And this is no longer used for weather forecast, but only used for research. And there is online coupling and offline coupling. So online coupling means the chemistry model is included as a subroutine of meteorological model. So chemistry and meteorology are resolved at the same time, simultaneously. So aerosol to cloud feedback can be simulated. But on the offline coupling, once meteorological simulation is done, then using the meteorological field, we calculate the chemistry and transport in the separate model. So, but in that case, you can easily use the other meteorological model, such as WRF. This is a global standard model developed by United States, or ASCA is a current generation weather forecast model of JMA, and SCALE. This is also a Japanese model. Yes. So the feature of NHM-Chem is aerosol representations. So in the global standard model is in the center, aerosols are categorized into 3 modes called 8-chem mode, 8-chem mode, 8-chem mode, 8-chem mode, and accumulation mode, and course mode. So 8-chem mode is a size of several 10 nanometer, and accumulation is 100 nanometer, and course mode is 1 nanometer, several micrometer. And so the gas to aerosol conversion, aerosol activation as cloud droplets, or aerosol activation as ice nuclei, ice droplets, and rainwater, snow water, gravel, and precipitated underground, or dissolution of gaseous species to the rain droplets, or deposition, dry deposition of gas, dry deposition of aerosols. Those processes are solved. This is, sorry, I should make it earlier, but this one. On the other hand, we have 5 category mixing type model. So 5 category is accumulation mode is separated into 2 groups because there are light absorbing particles in the air and non-light absorbing, like black carbon or some organic carbon, dust particles. It can absorb a solar radiation and heat the atmosphere, directly heat the atmosphere. But non-light absorbing aerosols such as sulfate, nitrate, those are not light absorbing. So for the climate simulation, we should separate the 2 categories. And also in the coarse mode, there is mineral dust and sea salt particles. The mineral dust is light absorbing and non-hygroscopic, but sea salt particles is extremely hygroscopic. So this is also need to be separated. So totally we have 5 categories in the default setup. So this is a, yes. Mhm.
You do not have the segregation for the type of aerosols, is it?
Sorry, segregation.
In the B category, you do not separate the type of aerosol, is it? Or you have different aerosol type association also. So you take the bulk aerosol optical properties for different sizes, or you segregate them based on their type.
I don't understand the segregation. So
I mean, so
Mhm.
PM2.5 dust or sea salt,
Yeah.
like in the third category,
Mm.
do you also do this for the B category or not?
Category.
You separate type of aerosols
Yes,
in the
yes.
B
B.
one. B is 3.
B. Yeah, three.
Yes.
3. Yes, sorry. Yes. No. So in the close mode particle, in the 3 category, sea salt, we assume that sea salt and dust are internally mixed for the radiation. Yes. Thank you. Maybe external assumption can be done, but the mixing state cannot be considered. Yeah. Anyway. Yes. So in many countries in the world, you do not need to separate the sea salt and dust because the abundance are very different. But for Japan case, mineral dust particle are transported from China over the ocean. So we have to separate these categories. But in most of cases, you don't need. Maybe for India, maybe not. Yeah. So then, so what happens? Click the presentation. No, it doesn't work. Okay. So this is current activity. I'm a modeler, but I'm doing some observation at the top of a mountain here. The height is 870 meter. So it's close to the cloud base. And we have 2 base site. It's an elementary school, which is not anymore. And then with the collaboration with the people from National Research Institute for Earth Science and Disaster Resilience, for cloud and rain people, radar people, and from University of Tsukuba, they are operating the observatory. And here, the National Institute of Environmental Studies for cloud chemistry, aerosol and cloud chemistry here. Then, so we carried a container and instruments by helicopter because there is no way we cannot go by car to the top. So we used helicopter to carry that container. So, and then this is the scenery of Mount Tsukuba and our operation. And we just, the full operation just started in March 2023. And here, so we have to walk and carry the instruments here. And then here is some container. And then we have now SMPS, OPC, CCN counter, fog monitor, drizzle monitor, distrometer to cover the size spectrum, size distribution of aerosol and cloud and rain from several nanometer to several millimeter. And then we have radiometer, microwave radiometer, and aerosol sampling, fog sampling for the chemical analysis. We don't have any online chemistry, but filter sampling, and visimeter and AWS. And we also have polarized OPC to separate the dust, spherical and non-spherical particles, polarized OPC. and RIBUS for bioaerosols, and LiDAR. Yes. Yes, that place is already there. The power is already there because it was a meteorological observatory belonged to JMA until 1970. We still have power there. Yeah. But it's not strong enough to, durable enough to handle lightning. So it often shut down electricity. Okay, so this is the, so the main, here, yes. Yes. So 1 year before that, yes, before that only meteorology.
Only meteorology.
Yes.
So this is the new development, basically, I
Yeah.
would say.
Yes. Using the building.
So, and also, what is the long-term plan, whether this will sustain for 5 year, 10 year, or?
So the project is 5 years, but not anymore. So I need to write proposal many times.
And this is funded by only JMA,
No, funded by
MRI.
my personal budget, not my pocket money.
Yeah. Project.
Personal project.
So it is not MRI.
Not MRI.
I see. Oh.
So it's a granting aid.
Yeah.
in
Okay.
Japan. Yeah. So I try to maintain as long as possible. So Akash project. So this is a project. So this is the 5-year project plus 2 years, so 7 year, including pre-research period. Then ended by next month, so March 31. And then the final workshop will be held in Delhi in the second week, so 12 and 13 of March. So if you are interested, you may have a chance, maybe ask Naja-san to join, maybe. And then this is the ultimate goal is to stop crop residue burning in Punjab by installing new agriculture technology for the better air quality in North India, including Delhi NCR. So the project consists of 3 parts. The first one is agriculture, and the second one is atmospheric science. So I am a leader of this group, but actually Patra-san is a real leader. I am the leader on name, and some public health. But due to COVID, the public health people cannot come to India to do some epidemiological survey. But the group, but anyway, so, and the background of research, you may know very well that in the atmospheric viewpoint, so the Punjab people thinks that the high concentration in Delhi is a local emission in Delhi. But on the other hand, in Delhi people, this is extremely high concentration is due to the crop residue burning in Punjab. So, and however, in the previous studies, the contribution of crop residue burning, CLB, in PM2.5 in Delhi varied substantially from 7% to 78%. So negligible or, I mean, very, it's very much depending on years and the selection of emission inventory. This is done by Kasworth et al. 2018. And this is very difficult. So why it is difficult? So there are mainly three reasons. And there are several factors which caused this large uncertainty. So fire emissions are usually detected by satellites, but if there is a clouds or thick hazes, they obscure the fire detection from satellite. And also, the polar orbit satellites pass that region only twice per day around noon and midnight. So duration of each fire is only for a few hours. So, and some farmers ignite fire after the sunset to avoid police control. So the diurnal variation is unknown. And also ground-based monitoring stations, CARCM or CPCB, we call, you have lots of dense air quality network over the India, but most of the stations are situated mainly in big cities and not in farmland. So we do not know the emission amount in the Punjab region. So in the project, we distributed the low-cost sensors CUPI-G to measure PM2.5, CO, NO2, OX, it's a ozone plus NO2, over the farmland regions like here, Punjab, Haryana, and some in Delhi. And I think that Narendra Singh-san installed CUPI-G to this campus. Or, okay, he's not here today. Yes. So I saw CUPI-G here, but we didn't use that data. We only focus Punjab, Haryana, and Delhi. And then this is an example. Then okay, so this is the fire emission underestimated in the presence of clouds or thick haze. So this is the G-fast CO emission detected, produced by, made by satellite data. And this is the November 1, 2, 3, 4, and 5. So in the November 3 and 4, the PM2.5 concentration in Delhi are very high, like 500 microgram per cubic meter on November 3, but there's no emission, not much emission detected by satellite. But if you see the MODIS AOD, aerosol optical depth, the data is not there in the presence of cloud. So emission is substantially masked by clouds. And also, the study is done by Lee et al. 2020. They reconstructed the fire emission based on a household survey from over 2,000 farmers in the region. And then, based on the survey, they create the diurnal variation. So MODIS satellite passing time is around noon here, but there is some continuous fire after 14, 18 until midnight. So in considering the diurnal variation, they boosted the emission by 361%. So this is their conclusion. And then, so this is the simulation and the observation comparison. So this is CARCM or CPCB station average data, and black is observation, and red is simulation with G-fast emission, one of the emission of fire, original fire inventory, we call it. And then this is the station mean PM2.5 in Punjab state and Haryana state and Delhi. And then on the right panel, this is a CUPI-G low-cost sensor station mean PM2.5 in the source region, as I showed in Punjab, and intermediate Haryana and Delhi NCR. So in the same period, it's from October 20 to November 14. And so for the government stations, so there is not so much, enhancement in this CLB period in this data. And on the other hand, in the farmland, there is some enhancement here compared to the simulation. And then there is a sign of urban, the Diwali day in October 24. So there's an enhancement in the observation. Observation is black. So there's an enhancement here. But in CUPI-G stations, Mhm. Yes. Yeah, this is from maybe burning, crop residue burning, most likely. So even though in the cities in Punjab, there's a plume from farmland. So because there is no enhancement in Diwali, so the selection of location of CUPI-G is good to avoid urban signals. And also in Haryana and in Delhi, there's sign of Diwali, but in CUPI-G there is no. Of course, in Delhi CUPI-G stations, there's some signal, of course. And then, so in the downwind region like Haryana and Delhi, we found two big plumes coming from Punjab during the period. So Singh et al. I didn't write, but yeah. Yes. So I will show you later, but GFAS emission significantly underestimated the emission, especially for CLD in this region. Maybe due to the different emission factor as assumed.
Many parameters, because there are several factors. It depends on the several factors,
Yes,
and
yes.
the inputs may not be that much high, so that the model cannot predict it, right?
Yeah. So the motivation is to yes. Yeah.
But for Haryana, Delhi, model and observation is not matching. What could be the reason?
Baseline, yes.
Yeah.
Which one?
Yeah, if you see that Punjab is almost matching, observation and your simulation is matching. But if you see Haryana and then Delhi NCR region, so there is discrepancy. What could be the reason?
There are many factors, but we do not how to say, we do not identify the reason yet. But to me, the model performance is similar with each other. This is my expert judge, but yeah. So
Like for Punjab, you say, so this might be the observation at particular point, one sensor.
one sensor.
Is it so?
So this
Like
is
the
average.
yeah,
of-
it is average or one station data
No, sorry, it's average of all stations in the
in Punjab.
states.
I
So
see.
like
Oh,
it's maybe 7 stations,
mhm.
and
Okay.
20 stations, 50 stations.
Okay.
And those
No,
are
so what I
10,
suspect,
10.
like you say in Delhi NCR, so average of say 20 sites. So those sites might be from very highly varying concentration and also low varying. So variability is very large. Probably. Okay.
Variability among the sessions. you mean?
Yes.
Yes. Yes. Yes, this is the left
UAC
one.
is Q, and this is the one observation.
Pollution control board. Yes.
Hello. So how many sensors were placed to have mean CUPI-G values which you have on the right hand
On
side?
the right hand.
Yeah.
Okay. I don't remember exactly, but around totally 30 stations. So maybe 10, 10, 10. But we can have it in the previous slide. This one. Or more than 10, yes, sorry. Yeah. So yeah, 15, 10 and 5, like that. Yeah. Yes. No, no. Yeah. It's obvious from the signal of Diwali. Yeah. Let me proceed to the next slide. So this is the model simulation domain of NHM-Chem. And then the domain 1 covers whole India with a horizontal grid resolution of 30 kilometers. And we have the second nested domain with a grid resolution of 6 kilometers. And then we used the station data in those 3 states. And square indicates the location of CPCB stations. And a blue one is CUPI-G source, and intermediate in green, and Delhi in orange. And there's so we are here now. So the Nainital is included in the model domain. Yes. In the domain, yes. But if the wind is coming from the east, it's not enough. But you say that the wind is mostly from westerly and southwesterly, so it should work, I hope.
And also I saw that your Reese emission data, resolution is the quarter degree, 0.25.
Yeah.
So it is, I think, new version that means. Earlier
Yes.
version was having 1 degree or
1.5 maybe.
Yeah.
Yes.
So this is the new version.
New version.
Kajino-san, what is the year? So this is for 2022.
Yes.
So this is only for October, November month in 2022.
Yes. But as I said, I also simulate 2019 and 2014 for my friends. Yeah. For the same domain. I always use that domain.
So both 30 and 6 kilometers.
Yes, 36.
Okay, so I think that would be comparable.
Okay, good.
Yes.
Yes. And Naja-san, and then you can see that the performance of Reese is not so bad as shown on the PM2.5 time series. And then, so I used the optimization using CUPI-G data, the emission inventories for the second domain. So it's a bit complicated to explain, but I set this following cost function to minimize. And then we change X value to minimize the cost function. So X is the enhancement ratio of the emission sources for 5 region tags and time tags, day and night. So we have 5 area tags like North Punjab, West Punjab, Central Punjab, East Punjab, and South Punjab and North Haryana. So the emission source regions. So we alter emission enhancement ratio or decrease. And also we alter the daily emission and nighttime emission to see somehow the diurnal variation. So it's not hourly. Hourly is perfect, but
Then in Reese you have the daytime and nighttime emission.
no, in the GFAS, so the tag. So we have night tag and the day tag, or tagged simulation. So and then, so this is again the result. So the left panel is the whole station mean. So this is the CPCB and CUPI-G stations. All station mean time series in November 2022 from November 1 to November 14. And during that time, we have plume 1 here, like 3 to 4. And we also have plume 2, like here, 10 to 11, according to Singh et al. 2022. And then, so the red one is the fire, total simulation. The black one is observation, and the red one is total simulation. And blue one is without CLB emissions. So, and then using the GFAS, so because the GFAS emission is very underestimated, so there's almost no enhancement. And then after the optimization using the CUPI-G data, we get some results over here. So red one is optimized fire emissions using optimized fire emission, and blue one is no CLB run. So the optimization was successful to enhance the PM2.5 in the first plume here in Punjab, Haryana, and Delhi to some extent. And also it is good here in November 8 to 9. But there is no enhancement here in Punjab, in Haryana and Delhi. And this is because, sorry, it's perpendicular, but this is because the meteorological simulation failed during the plume. So at that time, the air is convective and precipitation is there. So the movement of air is a bit complex and the simulation is not successful. So this may be the main reason for that. And this is the source contribution, the time series of the contribution. So the gray is the anthropogenic PM2.5, and red is the PM2.5 from North Punjab, from West Punjab, from Central Punjab, East Punjab, South Punjab and North Haryana, and other fire areas, except blue. Yes. This one, LBFGSP solver.
Right?
Mhm.
You have used the optimization technique to enhance the
Yes.
performance of GFAS because
Yes,
it gives
yes.
it usually gives your underestimated value of this. So could I know what criteria have you used for optimization? Means what criteria because like when we do optimization, we must be knowing about the meteorological condition over that place as well as your means basically meteorology we must know, and the aerosol science bit of boundary layer and aerosol science we must know before we choose a optimization technique. So I would like to know why you have landed up to this optimization technique for that reason.
Why do I use that?
That
optimization?
particularly that optimization method to, yeah.
Okay. The reason why I choose this optimization is due to my colleague. My colleague often use that technique, so I also use that. This is the reason. And for the meteorological parameters, this is all derived from the meteorological model. So it's not observation.
Yeah, this I have understood.
Yes.
Because like GFAS, how much, what is the, it underestimates the aerosol value concentration, whichever aerosol component you take. But the thing is like we don't know to what level of uncertainty is that. Means what is the percentage?
Yeah.
So even I haven't seen in your talk like what was the
underestimated percentage, and to what level optimization has improved it? Means like suppose the underestimated
Okay.
it was like 50%, and after using the optimization technique, the performance level was enhanced to this percent.
Okay. Okay.
So could you give me that figure? Is it possible?
Of course, yes.
Yeah.
Not in
Thank
my,
you. Yeah.
in the paper.
Oh, it's
I
in the
show
paper.
Yes.
Okay, okay.
It's
Okay, then.
under review, but there's one reviewer asking that similar with your question. So I'm answering. But also, this optimization is really depending on the magnitude of uncertainty in the observation. So I need to.
Exactly, because when you assimilate a model, the model inputs uncertainty also matter. And once the model gives you a result, I'm just interested to know that after optimization of GFAS, how good you miss, what was the enhancement, performance enhancement?
Yeah, okay.
Yes. Yeah.
So I don't have the exact number in this slide, but yeah, you can see, yes, rough idea. Yeah. Yes. So roughly speaking, the optimized emission is 7 times more than the GFAS emission. This is a rough image. Of course, it depends on the time and the region, but yeah. And people suggest to use a recent version of FIN for that region. This is better. Yeah. So they investigate the emission factor really suitable for the CLB in this region. Then if we use the PIN, then the standard simulation may be better. Yes. And then this is a comparison of the domain 2 total CLB CO emission. The left hand is GFAS. The unit is gigagram CO, 12 hours. So it's like a day and night. And then this is a time series from November 1 to 15. And the right axis is the optimized fire emission, gigagram, the same unit, but different axis. The left is the maximum number is 15, and the right is 100. So about 6 to 7 times difference. And so, as I said, that the serious underestimation of GFAS in that region for the CLB case, this is already well-known issue, but it was resolved. Like the left is, yes. And also, there's gaps in the GFAS emission, like November 8 and November 10, due to the clouds, was recovered by the optimization using CUPI-G like this. So it looks like natural variation. I don't know if it's really natural or not. And I want to also say that the diurnal changes in emission may be different day by day. So sometimes nighttime emission is larger than the daytime, but sometimes nighttime is smaller than the day. So in the previous simulations, they assume the same diurnal variation on the different days, but may be different on day by day. Yes, and so this is the summary of the CLB contributions to surface PM2.5 in each state. So in the plume one is divided into 2 phases. The fire emission travel from Punjab, Haryana to Delhi, and then further to Uttar Pradesh, and then it is again coming back from Uttar Pradesh to Delhi to Haryana. So plume 1A, so about 50% of PM2.5 was calculated as estimated as the CLB origins. And then on the returning plume, the effect is like 30 to 40%. And then in the plume 2, A is 8 to 9 November. Due to the fails in the meteorological simulation, we do not know, but only 55% in the simulation CLB image contribution. And then again, plume 2 is similar to plume 1, the direct transport from the northwesterly, and then the contribution is about half. So this is our main conclusion. And then as an appendix or supplement, I have a comparison with other independent observation data, Aeronet. Sorry that the Nile Tower is Skynet also, but in that region, I selected Lahore, the AOD, and Amity University Gurgaon, 2 sites. And then the top one is, well, what is it? Okay, so I have 3 types of optimization, so not much difference. But pink is GFAS and red is optimized one and AOD, and this here. So it is AOD is generally underestimated by NHM-Chem. This is we realize that issue, and due to the size distribution of aerosols or vertical profiles of aerosols, we do not know yet, but we need to resolve it. But anyway, this is the comparison with independent data, and also we have year-goals data, the commercial aircraft observation data. Okay, so this is year-goals, and then during the period we have six flight data in November 4 in the night, and November 7 and November 11 during the plume 1B, no plume period, and plume 2B period. And above is the CO concentration, and the below is ozone. And then so the black one is the observation by commercial aircraft, and then red one is optimized simulation, and blue one is CLB, non-CLB emission run. Then, as you can see, the triangle is the CPCB surface emission data. So the all flight is in the night. So ozone concentration is almost 0 due to the titration by NOx, NO. But in the above, there's some ozone there. And then there's some enhancement of ozone up to 1 kilometer. Like here, the ozone concentration doubles. So there is some impact of crop residue burning of ozone in the upper locations and CO2. Yes. And then, so okay. So the next slide is the final slide for the possible future collaboration. So Akash will be ended soon, but I need a budget for my personal post-Akash project. So I obtained PM2.5 filters in IIT Delhi, Delhi campus, and the Sonipat campus in PM2.5, and I brought it to Japan and keep in the fridge. But I don't have a budget for the chemical analysis, so now I'm writing a proposal for the aerosol cloud radiation precipitation interaction study in India. So if I get it, then it will be a 3-year project starting from next April. Then under the project, there is a post-group collaboration. Maybe the Naja-san has a mobile observation car. So plume chasing, mobile PM sampling for the chemical evolution, study of SOA and their toxicities, aerosol toxicities. So if you can get the sample from Punjab to Delhi, you can get how aerosols compositions are changed or aerosol toxicity are changed, or they are transported from the Punjab to Delhi. And also to chase the urban plumes, you already did it for the gaseous species, but the same thing for aerosols from Delhi to Nainital, and like this. And also, Priyanka-san group has a Wolfgang model. So we can have the multi-model analysis using the two models, different models. And also, I'm suggesting the exchange of observation data, Alice and Mount Tsukuba. If you are interested, then we can have also the same study for the Japan. Yes. So this is the end of the slide. So thank you very much for your attention. So if you have a chance to come to Tsukuba, then please tell me. I will take you to the mountain observatory. And this is a view from the mountain. This is my favorite picture. So here is a Tokyo area. So Tokyo, there is a haze below the cloud. So aerosol cloud interaction is going on there. Yes. Okay. Thank you.
Thank you very much, KAJINO-san, for this absolutely nice talk and shedding some light on the crops residue burning and optimizing emissions with the observations, which has not been done much. So if there are any more questions, we can take up a few.
I have one query and one question. Query is now the Mount Fuji station is now totally closed or
Still running.
running?
Yes.
So maintained by GMA or
No, also JMA give up
I see.
operation.
Okay.
Yeah, Mount Fuji and Mount Tsukuba also.
No. So Mount
But-
Fuji, who is operating then?
NGO, so national non-governmental organization,
I see.
mostly researchers.
And what observation they are doing? Only meteorology or some aerosol or chemistry?
So yes, so like SNPS,
Oh,
like Professor Miura of Tokyo Science University,
okay.
or Okochi in Waseda University,
Mm.
also cloud chemistry. So some observations there. However, Mount Fuji is a bit too high for
Yeah.
me for the aerosol cloud interaction. Yes. So we prefer this mountain. Enough low, close to the cloud base. Accessible. The Mount Fuji is accessible, but yeah,
But not throughout the year.
not throughout the year. Yes, only in the summer.
And can you go to slide number 15?
Yes.
Yes. Here I was seeing, if you see in the or optimized run, so of course there are some agreement, the peak, but I'm seeing the peak is also slightly shifted, like enhancement is also seen later on. Like observation says the peak and then, but the optimized run is seen the peak later on also.
Yes.
So what is the possible reason for that?
Yes. Optimization is limited because I only set the 5 region tags. And
I
in each
see.
region, the spatial distribution is based on the monthly mean GFAS emission.
Okay, okay.
So if you have more variety in the tags, then you will get more consistent result. Yeah, maybe.
And and also apart from the GFAS, did you try with GFAD?
No.
So any reason for, because what I have seen our previous experience, there is significant difference between both.
Okay, yes.
And also like over the India, I have seen they are also not consistent in the bias, like we compare with our observation, like in some region, in some season, G phase is positively biased, and in some region it is negatively biased.
Yes.
So I'm not saying inconsistent. So but you didn't try with the GFED.
Yeah, we tried, in fact, we tried the GFED and also FIN
Okay, yeah,
before,
yeah.
but how to say, I don't have any reason to select GFAS.
Okay, okay,
But yeah,
okay.
but I compared the emission amount
Yes.
in this season, FIN, GFAS, GFED, QFED, and so on. So, but not simulation.
Okay.
Compared.
Okay.
Yes, and GFAS is the minimal, but
Also, Kajino-san, you used CO emissions for comparison
Yeah,
between
yeah.
the optimization of,
yes.
but you also must have had observations for comparison, right?
I'm sorry for my tricky presentation,
It's
but
okay.
I only used PM2.5 but that
Uh-huh.
in the current state because CUPI-G CO data is not finalized yet.
Okay.
Yes.
So maybe in future.
In future. The
Correction
PM2
factor has to be put in.
Sorry?
The correction factor has to be
Yeah.
finalized.
Yes, yes. At that time, yes.
Yes, I just want to know what are the input parameter for your that NHM-Chem model for that aerosol cloud interaction.
Input.
Yeah, input parameters.
For the aerosol cloud. Okay. So for the CCN, so the size distribution and the hygroscopicity. Is it what you're asking?
What are the input parameters? As you have shown that aerosol cloud interaction chart. So what are the input parameter you are feeding in the model that you are non-hydrostatic meteorological model, CHEM model? So what are for the aerosol cloud interaction study?
Okay.
So
So for the CCN concentration, cloud condensation nuclei, we have to know the size distribution of aerosols and then hygroscopicity. And for the ice nuclei, we know the number and the surface area and the ice property. And then for radiation, the refractive index and size distribution also. So all those parameters are input parameters. So am I answering?
So
While doing the optimization, so how do you, what method you have? This is linear optimization or what?
It's not linear. It's sorry, I'm not familiar with the optimization method, but this optimization method can be applied for any nonlinear equations.
Oh, this is non-linear.
Yeah.
Directly, it's not linear.
Yes. So I cannot go. Yes,
It's fine. It's fine. It's fine. That's I just wanted to know. That's linear or non-linear.
it's nonlinear. Yes.
as far as I remember, it was the difference of the squares. So they are just minimizing the measurement and the observation bias, and then seeing where they get the minimization with the model parameter. So it would be non-linear. It's not like a linear. Right.
Yes.
Right.
Yes.
Okay. So if there are no more questions, I would like to thank Kajino-san for this nice talk and giving us a chance to discuss all the results. And also, I think he has given us a good opening for collaboration and a good starting point from where we can build up, and we would surely discuss afterwards about it. So I would like to thank Kajino-san. So first of all, we can give him a good round of applause for conducting this nice talk at this length. And I would also now like to invite uh, our director, Manish sir, to present a small souvenir
Oh.
to Kajino-san for this. talk.
Oh, great.
Seeing tomorrow.
In the 3,000-meter place?
Yeah,
Oh.
3,500. So this
Oh.
is that telescope you can see.
Very nice. Yeah, thank you.
はい
どういたしました。
if-
そうだ。These are 4 meter.
Yeah,
3.6.
3.6.
Okay. So thank you very much, everyone.
3.6.
And thank you, KAJINO-san.
Thank you. Okay, yes.